Hello everybody, welcome to Chemistry 101, where we will be talking about chemistry. Today's topic with regards to electrochemistry is oxidation and reduction. After this video is done, you should be able to define oxidation and reduction operationally and theoretically. You should know how to differentiate between redox reactions and other reactions using half reactions and redox numbers. Also, you should know how to identify electron transfer, oxidizing agents, and reducing agents, redox reactions that occur in everyday life, in both living and non-living systems. Lastly, you should know how to compare relative strengths of oxidizing and reducing agents using empirical data. Redox reactions are reactions that involve the transfer of electrons in a reaction. Redox reactions must involve both oxidation reactions and reduction reactions. Historically, the term oxidation referred to the chemical reaction of oxygen with other substances, such as the reaction that occurred in combustion. Reduction was historically defined as the process of reducing metal compounds to pure elemental metal components. Nowadays, the definitions for oxidation and reduction are much more defined. In terms of electron transfer, oxidation refers to the loss of electrons in a reaction. Reduction refers to the gain of electrons in a reaction. Redox reactions are involved in a number of processes, including cellular respiration, photosynthesis, combustion, as well as corrosion. Redox reactions are also used in industrial processes, such as electroplating metals and manufacturing of electrochemical cells. Electron transfers that occur in redox reactions are not limited to just the laboratory or fuel cells. They are also used in living systems as well. Without redox reactions, producers like plants and algae would not be able to use the sun's energy for photosynthesis. Without photosynthesis, entire food chains would collapse. There will be no oxygen to breathe. Let us recall the basic chemical equation of photosynthesis, in which light converts carbon dioxide and water into sugar and oxygen. When sunlight strikes a molecule of chlorophyll, it provides the energy needed to excite an electron and release it. The electron is captured by the primary electron acceptor, which is then reduced. The chlorophyll loses an electron and is now oxidized. The primary electron acceptor now has an extra electron. It is now an electron donor and ready to be oxidized. The electron continues to move between the compounds until it is finally reduced to the complex molecule of NADP, and then it is reduced into its higher energy form, NADPH. This movement of electrons through the electron transport chain is governed by the same principles as basic redox reactions. Photosynthesis releases oxygen into the atmosphere, creating an oxidizing environment. It is this oxygen, in combination with moisture, that provides the conditions for a commonly recognized spontaneous redox reaction, corrosion. Corrosion is commonly thought of as the breakdown of metals. When a metal is exposed to the environment, electrons are pulled away from the metal atoms by oxygen, and the metal is oxidized. The metal acts as a reducing agent. The tendency for a metal to corrode depends on its oxidizing potential. Some metals, like gold and silver, are very weak. They corrode very slowly, if at all. Other metals, like aluminum and iron, are strong reducing agents and corrode very easily. The corrosion of metal creates structural and economic problems. Knowledge of electrochemical principles can help reduce and prevent corrosion. For example, aluminum oxide, formed when aluminum corrodes, adheres tightly to aluminum metal, preventing the oxygen from further reaching the aluminum. Iron oxide, on the other hand, flakes very easily from the iron metal, further exposing the iron metal. Today, industries have many methods to prevent corrosion. If oxygen is prevented from reaching the metal in the first place, oxidation cannot occur. A coat of paint, sealant, or even a thin layer of second metal will protect this metal. Galvanization is a special term given to the coating of iron with zinc. Nails used in construction projects that will be exposed to air are usually galvanized. Although they are a bit more costly than regular nails, they will last a lot longer. Electrochemical cells are used to harbor the electrical current generated by chemical energy produced in a redox reaction, which can then be converted into electrical energy. An example of this are batteries. As you can see, the cell separates this overall net equation to two sides. We have solid copper and silver attached to the wire, and their respective ions are in the solution. The silver and copper will either go oxidation or reduction. The electrons lost by one metal will travel along the wire to the other side and accepted by the other. You may have noticed that the two species are separated into two halves. Half reaction splits up an overall reaction to illustrate the gain or loss of electrons by one of the reacting species. Let's take a look at an example. The following net equation can be broken down into two half reactions. Here, solid copper reacts with a silver ion to form a copper ion and solid silver. Let's take a look at how we can break this down. In this equation, you can see that solid copper decomposed into a copper ion, and in doing so, it lost 2 electrons. In the second half reaction, we can see that the silver ion gained 1 electron to form solid silver. Since silver has a charge of 1 and copper has a charge of 2, that means for every 2 electrons that the copper gives up, it takes 2 silver ions to use up the 2 electrons to form 2 atoms of solid silver. The species that gains electrons causes the other substance to oxidize. Therefore, we call it the oxidizing agent. Since the other species is oxidizing, this species must be the reducing species itself, and it accepts electrons from the other species. The species that loses electrons causes a reduction of the other species, hence we call it the reducing agent. Since the other species is reducing, the reducing agent must be oxidizing itself, and it does so by donating electrons to other species. In the following net equation, the one we had earlier, which is the oxidizing agent and which is the reducing agent? Well, in the first half reaction, we can see that there is a loss of electrons, and the copper undergoes oxidation. Hence, the copper must be the reducing agent. In the second half reaction, the one with the silver ion, we can see that it has gained electrons and undergone reduction. Therefore, we can theorize that the silver ion is the oxidizing agent. Let's take a look at our electrochemical cell from earlier. We theorize that the solid copper or oxidizing species is giving up electrons. The electrons are then going along the wire to the side with the solid silver, which accepts these electrons. Copper, having lost its electrons, is now an aqueous ion and dissociates into the solution. Silver, having gained an electron, reduces into the solid silver metal. Let's take a look at another example. In the following net equation, we have liquid bromine, which reduces into its ion form, but at the same time, it has undergone oxidation into bromate. Now, identify the oxidizing species, the reducing species, oxidizing agent, and reducing agent. First of all, before you freak out and say, there's only one reacting species, this is not a redox reaction, let me assure you, it is very much so. If you take a look at your table of standard reduction potentials of half cells, you will see that the bromine atom appears on both sides of the table. It is formed when the bromate ion reduces. However, since bromine is the one on the left side of our equation, I am now going to flip the arrow for our first half reaction. Now, as you can see, bromine undergoes oxidation, and therefore it acts as a reducing agent. Let's take a look at our second half equation. Here, bromine gains 2 electrons to form the bromine ion. Bromine undergoes a reduction, acting as the oxidizing agent. Now, how does that work? The previous example is an example for a disproportionation reaction. A disproportionation reaction is a redox reaction in which the same species is both reduced and oxidized. Bromine is both reduced and oxidized, hence it undergoes disproportionation. Now this is a table of relative strengths of oxidizing and reducing agents. By placing one substance in direct contact with another and observing whether or not a reaction occurs, the relative reducing strengths of the two can be found. This table shows how the strength of oxidizing agents on the left side increases going up. They have a greater tendency to gain electrons. As you go down, the strength of the reducing agents increase. They are more likely to lose an electron. Strong oxidizing agents have a natural tendency to accept electrons, and strong reducing agents have natural tendencies to give up electrons. When they mix, we call this a spontaneous reaction. However, a weak oxidizing agent and a weak reducing agent are unable to react on their own, for they do not have enough energy to make the transfer. Finally, it is also impossible for two oxidizing agents or two reducing agents to react, for when they mix, they will want to either both gain or lose electrons, but they will have no particle to receive or donate electrons from. Now, let's take a look at another example. Which of the following equations will yield a spontaneous reaction? Well, the first thing to do is to determine which is the oxidizing agent and which is the reducing agent in the reactions. In the first equation, the gold ion can only be reduced and the fluorine ion can only be oxidized. However, the fluorine ion is above the gold ion on the table. Since we have a strong oxidizing agent and a weaker reducing agent in comparison, the fluorine does not have enough energy to give up its electrons. In the second equation, all looks good since our oxidizing agent permanganate is well above our reducing agent hydrogen peroxide. However, upon second glance, permanganate needs hydrogen ions to react. Since there are no hydrogen ions in the equation, the reaction is non-spontaneous. Now let's take a look at our last equation. It may first appear that we have two oxidizing agents. However, the Fe ion can appear on both sides of the table. With this, we can see that our oxidizing agent, chlorine gas, is above our reducing agent. We have a strong oxidizing agent that is above our strong reducing agent. This reaction will go forward. I hope this video has been helpful and that you are more confident with your understanding of electrochemistry. Thank you for watching.